So guys, in the last class, we had discussed about cycloalkanes and cycloalkenes, naming different rules what are associated with cycloalkanes and cycloalkenes, and we have seen a lot of examples. Now, today we'll talk about remaining few structures, or you can say cyclic structures or alkene kind of structures, where we need to understand the way of naming. These are almost like the last part of the simple carbon chain naming. Simple carbon means that when there is no functional group present. After this, we'll be starting functional group. So we have spoken about a lot of side chains, like we had spoken about alkyl groups, we had spoken about alkenyl groups, we had also spoken about alkynyl groups. So all these were branches. Alkyl group were the branches with all single bonds. Alkenyl group were the branches where we had double bond, basically alkene when acting as a branch, and that was alkenyl group. And when alkyne acting as a branch, it was alkynyl group. So there is one more type of branch which we need to understand and which we will see in many of the cases, and that is alkylidenes. These are also side chains, or these are also branches. So what exactly these are, let's understand. When you talk about alkenyl groups have carbon-carbon double bond in that branch itself. Whereas when we talk about alkynyl group, there is a carbon-carbon triple bond in the branch, right? And here, now when we are talking about alkydenes, what exactly are alkydenes? Alkydenes means there is a principal carbon chain. Okay, so I'll just write it on the screen. Just check. There is a principal carbon chain. Okay, this is my principal carbon chain, and this is connected to a branch with a double bond. So branch which is connected with the principal chain using the double bond. So the branch doesn't have double bond inside, as in like the carbon of branches are not doubly bonded, but the branch is connected to the principal carbon chain using the double bond. Then that group is called as, then this branch with the double bond is called as alkylidene. This can be any length longer carbon chain, by the way, right? So I can also write it as double bond and R group. R means nothing else but any length longer carbon chain. Double bond represents that your branch is attached to the principal carbon chain using not a single bond but a double bond. Like when we talk about alkyl groups, we generally represent them as dash R or single bond R. That means this R group or carbon chain is attached to the principal carbon chain or the parent chain using the single bond. Here alkylidene is double bond R, which represents that the branch is attached to the parent carbon chain using a double bond. So now this kind of branch will be called as alkylidenes. Okay, so double bond R when attached to the parent chain as a branch, then it is called as alkylidene. And we have few examples here, like if I talk about double bond CH2. In that case, we have only one carbon, right? So the word root for this branch should be meth, and because it is alkylidene, the name will be methylidene, or we have another common name also for this branch. We also call it as methylene. Okay, so we can call double bond CH2 as methylene or methylidene, and this double bond CH2 will be acting as a branch. So that means principal chain would be something else, and no matter what, you cannot avoid this double bond CH2 acting as a branch. In any such circumstance, this will be called as methylene or methylidene. Similarly, if I have double bond CH3, now here you don't have to basically count number of hydrogens, or you don't have to remember the hydrogens. It's just the valency which has to be fulfilled by hydrogen. So I can write double bonds. If somebody asks me to make an alkylidene using 3 carbons, so I will just write 3 carbons first, and the first carbon which is attached to the principal carbon chain using double bond. Okay, now the remaining valencies will be fulfilled by hydrogen. So this will be this, and this will be this. So this is how the structure of three-membered alkylidene, right? Now, so I was giving you this example, double bond CH3, when acts as a branch or a side chain, it will be called as ethylidene. So what you'll be naming as R group is anyways called as alkyl, right? Single bond R group is anyways called as alkyl. Double bond R group will be called as alkyl, and then idenes. So what is alkyl? Alkyl will represent how many carbons are there. So here we had 2 carbons, so it will be ethyl and then idene. Okay, so this is our alkylidines. Let's see their uses and application in different examples. So let's talk about the first example. First example, what we have is a carbon chain over here with the multiple carbons. So where here we have in total double bonds in the in this carbon chain as 1, 2, 3, 4, and 5. Now we have to take such carbon chain which can include maximum number of carbons with maximum number of double bonds. We will try to keep as maximum unsaturated bonds in the principal carbon chain as possible. So the possibility is I can go this way. Okay, if I'll go this way, I will have 1, 2, 3, 4, 5, and 6 carbons and 2 double bonds. So one combination is 6 carbons and 2 double bonds. Okay. Another way is I can go this way. And this way will also give me 6 carbons and 2 double bonds. Whereas if I go straight, it will give me what? It will give me 1, 2, 3, 4, 5, 6, 7, 8, 9 carbons and 4 double bonds. So that's how we will be choosing our main principal carbon chain. Right? So this is my principal carbon chain. This is my principal carbon chain. And now no matter what I do, I cannot avoid this part acting as a branch. So if I simplify this chain, how can I write it? I can write it as CH2 double bond CH single bond CH double bond CH single bond C, uh, then single bond C double bond CH2, and then C H double bond CH single bond CH double bond CH2. That's how my chain would be if I'll simplify it. So this is my longest possible chain with all the double bonds possible. How many carbons are there? 1, 2, 3, 4, 5, 6, 7, 8, 9. So it's a non or nona structure. So see, when you talk about the word root, it can be non, it can be nona. Different questions you will find different things, but there is no difference in the name. Non and nona represents the same thing, so you can write either way. How many total double bonds we have? We have 4 double bonds, so it will be nona tetraene. Now I have left space because I have to fill the positions over here. So we can start marking it from either way. Because it is a symmetric chain, the numbering won't make any difference over here. So we will have double bond on first position, third position, sixth position, and eighth position. So we will write it as 1, 3, 6, 8. Very clumsy, I have written it over here. Let me just rewrite it. Let me rewrite it. It will be nona 1, 3, 6, 8 tetraene. And then what is the branch over here? This is the branch, double bond CH2. Double bond CH2, this is the branch. And we have already discussed what this branch is called as. This branch is called as methylidene or methylene. On which position does it exist? On the fifth position. So we will write it as 5-methylene nona 1368 tetraene. Okay, so this is how we are going to name the compounds carrying the alkylidenes as the side chain. So let's see a few more examples over here. Let's talk about this example. Now again, we will take this as a main chain, and this main chain has how many carbons? 1, 2, 3, 4, 5, 6, 7, 8, 8 carbons. So octa. We have to find out what are the positions of the double bond. We will start from here. Why? Because we try to give the lowest possible position to our first double bond. So if we'll count from here, my first double bond is going to get the lowest number. Overall also we try to give them the lowest number, but if I have a particular double bond on the first carbon, we will always try numbering from there only. So 1, 2, 3, 4, 5, 6, 7, and 8. So I have positions 1, 3, and 6. So octa 1, 3, 6 triene. On the fifth position, I have a branch which is attached to the principal carbon chain using a double bond, and this is carrying 2 carbons over here. So this structure is nothing else but basically this. This is the structure, and this structure which is attached to the principal carbon chain using double bond is an alkylidene made up of 2 carbons. So the name of this will be ethylidene. So that is why we have written 5-ethylidene octa 1, 3, 6 triene. Now let's go to the next one. In the next one, we will try to find out the longest possible chain. So you have to try all the combinations on your own, or better what you can do is you can stop the video and you can try out these questions on your own, though the answers are mentioned over here. Do not copy the answers. Just write the questions, note them down in a notebook and try out, see what answers do you get, and then we can compare it with my answers. Okay. So let's discuss what exactly these will be called as these structures. So we have possibility of going from left to right, taking this as a main chain. In that case, we will have how many carbons? 1, 2, 3, 4, 5, 6, and 7 carbons will be there. And how many double bonds we will be having? We will be having 1, 2, 3, 1, 2, 3 double bonds. Other ways we can go down like this and take this as a main chain. If I do it this way, again, I'll have 1, 2, 3, 4, 5, 6, 7 carbons with three double bonds. So how will we choose which is the main chain? Let's see. If I go from left to right straight, in that case, the numbering will be 1, 2, 3, 4, 5, 6, and 7. And my double bonds position will be 1, 3, and 6. Whereas if I go from top to down like this, number of carbons are not changing, total number of carbons are 7, and the position of double bond is going to be 1, 3, and 5. 1, 3, and 5. So which one is giving me the lowest sum? Because the number of carbon chains in the main carbon or the principal carbon chain are not changing, so there must be something which can help us in figuring out which one has to be taken as the main chain, and that will be the position of double bonds. So this is giving me higher sum, this is giving me lower sum, so I will prefer going like this rather than going straight, because this is giving me double bonds lower sum. Okay, so total 7 carbons when you are going from left to right and then top to bottom, and this is becoming hept 1, 3, 5 triene. And now you have to be very carefully, you have to see very carefully what exactly we are doing. So now we have a branch over here, but see whether this branch is basically your alkylidene or some other group. See, this is my branch. This is my branch. Okay, and this branch is connected to the principal carbon chain or the fifth carbon chain with a simple single bond, whereas a double bond is in the branch. So this is basically, this branch is nothing else, but let me just write it, simplify this chain. This is CH2 double bond CH, single bond CH, double bond CH2, single bond C, double bond CH, CH3, and then go straight. Then you have CH, double bond CH2. So this is the thing. We have selected this chain as our, let me just take a different color pen. We have selected this as a principal carbon chain. Okay, so it is clearly visible that this particular branch is not attached to the principal carbon chain using double bond. Instead, it carries a double bond inside. So this is not an alkylidene. Instead, this is an alkynyl group. This is an alkynyl group. I hope you would have understood what is the difference between alkynyl group and alkylidene. Alkylidene is the normal carbon chain which is connected to the principal carbon chain using double bond, whereas alkynyl group is an alkene branch. This is my alkene branch. So the name is going to be 5-ethanyl hept 1,3,5 triene. Let's look at the next question. Next question, we have the cyclic chain as the main chain and double bond CH2 as a branch. So name will be methylene cyclohexane. You need not to mention the position over here because the position is going to remain 1. Next question, again we have the cyclic chain as a main chain and this branch is connected to the main chain or principal chain using a double bond. So alkylidene made up of 2 carbons. So it will be ethylidene cyclohexane. So this is about alkylidenes. This is the last part which you have to understand as the branches, what all different kind of branches can be there in the carbon chain. Now we'll be talking about the next type of cyclic compound, that is bicyclo compounds. So now we are talking about bicyclo compounds. What exactly are bicyclo compounds? Basically 2 cyclic rings when they are fused together will be called as bicyclo compounds. So basically 2 cyclic chains connected together through the same wall will be called as bicyclo compounds. Okay, and now when you're talking about the connecting wall, which is the common wall between one cyclic ring and another cyclic ring, can have 2 carbons, minimum 2 carbons as the common carbons, and can have 2 or more than 2 carbons also. Minimum number of carbons which are going to be common between one cyclic ring and another cyclic ring are going to be 2. minimum. It is what, again I'm telling you, it is minimum. Maximum can be any number of carbons in that wall which is shared by one cyclic ring and another cyclic ring are going to be the common carbons. Okay, for example, let me just show you. If I say this is so let's say if I say I have an individual structure as this is cyclobutane, and I have an individual structure as this is cyclopropane. If I join these two structures and I make this compound. Okay, now two cyclic structures have been combined together, right? So this kind of compound will be called as bicyclo. Here the shared carbons or the common carbons are the ones which are on the edges, which are basically on the shared wall. So this carbon, let me just mark it. So this carbon and this carbon is going to be a common carbon in between. This carbon, the first carbon and the second carbon, is going to be a common carbon in between. We generally call these common carbons as bridgehead carbons. So this carbon and this carbon will be called as bridgehead carbons. Okay, now let me just show you one more example. Let's say if I take individually, this is my structure, okay, and I take these are two cyclic chains, assume, and now I want to fuse them together and make a new structure. The new structure will be, this is going to be my new structure, right? So how many common carbons do we have which are being shared by two cyclic rings? One over here, one over here, and one over here. So that, as I mentioned, you can have two or more than two common carbons between two fused rings, okay? But this one and this one, only topmost and the bottommost will be considered as bridgehead. I'm just writing BH. Center one will not be called as bridgehead. Bridgeheads are the ones from where the bridge is starting and where the bridge is ending. Okay, but when you talk about the common carbons, there are three common carbons. Okay. So here what I have shown here is a 2D representation of the structure. Now when you get in the paper or when in the different exams you will be encountering bicyclo compounds, you may get a 2D representation or you may get a 3D representation. You have to keep your mental eye open and you have to visualize how the structure looks like. Okay, for example, I have taken the first example as cyclohexane, which is divided from inside. Basically two cyclic rings have been connected together, okay, and there are three common carbons, one here, one in the center, and one at the end, and the topmost one and this one will be called as bridgehead. As I mentioned, bridge starts from one head and ends at another head. Now if you actually want to see how this will be, so your cyclohexane, basically it's like you have five membered ring. You can call it as basically two rings are there. This is ring one and this is ring two. First ring has 1 2 3 4 5 carbons, and second ring also has 1 2 3 4 and 5 carbons. So basically five membered carbon rings have been fused together, which actually look like as if somebody has done a partition on a cyclohexane. If you actually look at its 3D representation, the 3D representation will look like this. So now let me just show you how this structure will look in 3D. I showed you over here, this is the 3D structure of it, but how exactly it is 3D, let me just show you. The 3D representation of this two five membered rings fused together is something like this. So you have a bent ring, okay, which is separated by a wall, or you can say by a, what do you call it, by a bridge. Okay, so this carbon, I hope you're able to see it. Just see. Okay, so here this carbon is going to be a bridge carbon. This carbon, okay, this carbon is also going to be a bridge carbon, and this is again a common carbon. So here if you consider one, so 1 2 3 4 and 5, this is one five membered ring. Okay, I hope you guys are able to see it. So this is one five membered ring, and there is another five membered ring like this. So this is my another five membered ring. I have just rotated it. I mean, you can see there is a hole over here. There was no hole over here. So basically, this whole one thing is one ring, and this whole one thing is one ring. So when you draw the 3D representation of it, of this a six-membered ring with a bridge in between, it is something like this. This is how it will look like, and that's how what exactly I have drawn on the paper also. So you draw it this way, or you flatten it, you make it a 2D structure, and you draw it the way I have drawn it over here. Both the structures are right. So a representation can be given in a 3D representation, a representation can be given in a 2D representation. Eventually, it can have multiple different ways to represent. We just have to know, or we just have to understand how many total number of carbons are there, how many bridge carbons are there, bridge head carbons, and how many total carbons are there in common. So you have to visualize thing. You do not have to treat it separately. See, mind it. Let me just show you one more thing. So basically, let me just color the different color this thing. Rings over here. This whole thing is one ring. Okay, this is one ring. This is something like this, which I showed you just now. This is one thing. Okay, this whole thing. So this is 1, 2, 3, 4, 5 membered ring. Let's see. Okay, and now this I should not have taken this color. Let me take a different color. So this is the another ring. Okay, there is a wall in between which has been represented as 3D like this, and then the two rings side by side. So basically this part and this part are two separate rings which have been separated by this wall. So this is the wall. Okay, so basically every time whenever you will be looking at a 3D structure, you have to be very careful while marking the carbons. So this is one carbon over here which is common, this is one carbon over here which is common, and this is another carbon which is common over here. So there you have to have a better clarity and a good visualization to visualize what exactly is happening. So it is like this is one a flat plane, and then top this is one ring, and then again this and this is the another ring. That's how it is. So this vertical wall is going to be a common wall. So you can have a 3D representation, you can have a 2D representation. 2Ds are easy to understand, 3Ds will take some visualization, but you have to think and understand it well. Okay, so I've told you what is bridgehead carbon. Now see, I'm showing you furthermore different type of 3D representation. Let's talk about the next example where 3D visualization is required. So this we have already discussed. Let's talk about this one. So this is another 3D representation what we have. Let's mark which one is the ring 1 and which one is the ring 2. So basically this part is my ring 1. This is my ring 1. It is like you have this as a thing, okay, and you had put this as a separator. That's how it is. So basically it is, this part is one ring, okay, which has two common carbons, and then total four common carbons basically, two as a bridge head and two are of the top ones, and then there are two here. I hope you're able to understand. So this is one ring and this is the another ring. That's how it is. This is one ring. Just see the separation. Okay, this upper thing is common in both, no matter you talk about this ring or you talk about this ring. So you talk about first ring or second ring, this whole thing is common. So four carbons are common, okay, which are on the corners, and two are non-common carbons in both the rings. So that's how the actual visualization is, or actual representation is. So there are, this is one ring, 1, 2, 3, 4, 5 and 6 carbons in it. Basically that's how I can draw my one ring, correct? And the other ring will be like this. This is my other ring, okay, and these two walls are basically, this wall and this wall is basically a common wall. So I have one carbon here, one carbon here, one carbon here, one carbon here, one here, one here, one here, one here. So in this vertical wall, which looks like this has four carbons which are common carbons and which have been represented by simple this one structure only. So basically these two structures have been merged together, right? So if I draw this, it's like this, right? And this flap or this vertical thing is common. So total four common carbons with two bridge heads, one bridgehead over here, and then one bridgehead over here. Total common carbons are 4. Two bridgeheads are there and two cyclic structures are there. Total number of carbons, how many are there in total bicyclo compound? 1, 2, 3, 4, 5, 6, 7, and 8. Mind it, this intersection doesn't mean anything. There is no carbon over here. Please understand. Intersections do not mean the carbons. You have to be very careful while marking the carbons. Okay, so you have to visualize. Without visualization, you won't be able to understand where the carbon is and where it is not, and then you'll start marking randomly. Okay, so these are some bicyclo compounds where two cyclic structures have been fused together with a common wall, which have some shared carbons, at least two, and those two which are starting a wall and ending a wall will be called as bridgehead carbons. Inner carbons will not be called as bridgehead, but the whole common shared wall will be called as bridge. Okay, so now let's see how to name these structures. Okay, so let's talk about the naming of the structure. Now, when you are naming the structure, you have to be very, very careful because you may get a 2D structure, you may get a 3D structure. First of all, you need to know how to resolve the structure. Okay, so when you are naming it, always remember numbering will start from the bridgehead and we will take the longest possible route to reach to the next bridgehead. So one bridgehead will always get position 1 and then we will travel throughout and then come back to our second bridgehead. Okay, for example, this structure can be represented as this in a 3D representation. This is 2D representation, this is 3D representation of the same structure. And when we are starting, I have started from here. This is my bridgehead. I have started one from here. Now basically, if you see, both the cyclic chains are symmetric. Two uncommon carbons are here, two uncommon carbons are here, and this is anyways the common bridge in between. This is the common bridge, so it really doesn't matter. I'll go from here to here clockwise or I go anti-clockwise, it won't matter at all. I start with this bridge head or I start with this bridge head, it won't matter at all. Okay, so you can take any bridge head, you can take top bridge head, you can take bottom bridge head. In this specific case, you go clockwise, you go anti-clockwise, it won't matter at all. You go from left side, you go from right side, it won't matter at all, but it will matter in many other cases. So I have marked the top one. This is my personal preference. You can take the lower carbon or lower bridge head as the first carbon. It is completely your choice. It won't make any difference in the answer. So I have taken this top one as the first carbon, then I have started moving as 2 here, 3 here, 4 here. This was the only possible longest route. Root is same from both the ends, by the way. Go to 4, 5, 6, and 7. So numbering the common carbons will be the last thing which are there in the wall. You will go through the continuous thing first, and then at last you will go to a non-continuous common carbon. Okay, so 1, 2, 3, 4, 5, 6, and 7. That's how we will number it. Similar way, if I talk about this compound, I'll start the numbering from here. This is 1. This is now here we have to be little careful about the numbering. We have to do the numbering in such a way that we take the longest route and come to the next bridgehead, but also we have to try giving my double bond as the lowest position possible. So if I'll go from this way, let's say from left to right, okay, then the numbering will be 1, 2, 3, 4, 5, and 6. Then you mark it 7 and you mark it 8. That's how will be the numbering. So in that case, my bridgehead carbon is getting position 4 and my double bond is getting position 5. Okay, whereas if I go other way, if I take other way 1, 2, 3, 4, 5, 6, 7, and 8. In this case, again my bridgehead carbon is getting position 4, which is same as the previous one. Along with that, my double bond is also getting the lower position. So I will prefer this numbering. Okay, so now look at the next case. In the other case, the double bond is there in both the sides and the whole system is symmetric. So you can start numbering from anywhere. I can start from here 1, 2, 3, 4, 5, 6, 7, and 8. So either way you can number. You could have numbered from left to right or right to left. Either way it is fine. Okay. Now how will we name these compounds? Now we have understood numbering. Let's see the naming procedure of these compounds. So naming will be done in such a way that first of all we will use a prefix called as bicyclo. The same way how for the cyclic compounds there was a prefix called as cyclo. Similar way for these compounds the prefix is bicyclo. So we will write bicyclo. Okay, and then total number of carbons. I'm just naming this compound first. So total number of carbons in my compound is 7, the above carbon which we have taken. I'm not talking about the two separate rings. We are talking about the total number of carbons in the bicyclo compound. These are 7, and hence the name will be heptane. So this space has been left in such a way that we are going to fill some numbers over here with some relevance. So basically, go to the first ring. Okay, if I talk about this ring, okay, this is my first ring. How many uncommon carbons are there in this ring? Let's see. 1 and 2. Two uncommon carbons here. Okay, let's talk about the second ring. How many uncommon carbons? 2 here. Okay, and then let's talk about the common wall. This is my common wall, right? And here, apart from the bridgehead carbons, how many carbons are there? Just 1. 2 are bridgehead and 1 is non-bridgehead carbon. Now these numbers we have to arrange in the square bracket in the descending order. So I got 2 uncommon carbons from here, 2 uncommon carbons from here, and 1 non-bridgehead carbon from the common wall. So I will write it as 2.2.1 in descending order. That's how we write the name of a bicyclo compound. Now let's see this again. Now let's see this example so that you get better clarity. So here again, how many carbons we have in total in the compound? We have 8 carbons, so the name of the compound will be octane. And as we know, this is bicyclo. Okay, now what to fill in this square bracket? Let's understand. Okay, my bad. First of all, I have done a mistake over here. Let me correct that. Mistake is I have written octane. It's not octane, it's octene. We have a double bond. So we will write oct to ene, okay, and bicyclo. And then in this square bracket, we have to fill the information. What information we have to fill? Again, from both the rings, how many uncommon carbons are there, and in that shared wall, how many carbons are there which are not bridgehead. So let's talk about this ring first. In this ring, how many uncommon carbons? 2. In the other ring, how many uncommon carbons? 2. In the common wall, we have 2 carbons which are not bridgehead. So the number is going to be 2.2.2. Here all the 3 numbers were same and hence no descending order. So we will write 2.2.2. Okay. Exactly same way. Let's try out the next one. So we have 8-membered ring. So let's write oct. We have 2 double bonds. One is on 2nd position, another is on 5th position. 2,4 diene. And because it is bicyclo, let's write bicyclo. And then we have to put some numbers in the square bracket. So number is again 2 uncommon carbons in one ring, 2 uncommon carbons in another ring, and 2 non-bridge carbons on the shared wall or shared bridge. So number is 2.2.2. I hope you have understood what we are trying to explain over here, what we are trying to do over here. Try out this on your own. Try out solving more questions on it and you will get better clarity. Let's see if we have any other question left. Okay, so this is the last one what we have. In this last one, again, we will first of all start numbering from one bridgehead. This is 1, 2, 3, 4, 5, and 6. We don't have any other carbon on the bridge. So total 6 carbons. The name is hexane. Then it is bicyclo. Okay, and then let's fill the numbers over here. How many uncommon carbons in the first ring? 1 and 2. 2 uncommon carbons. 2 uncommon carbons in the another ring also. And then in the bridge, is there any carbon without bridgehead? Which is not the bridgehead? No, 0 carbons apart from bridgehead. So dot 0. That's how will be the name. So these are some examples. You won't get any complicated things over here. These are the maximum complexity levels of the bicyclo compounds. If you have understood this, it will be easier for you to solve questions. There are no major changes which they can make in these bicyclo compounds. Here we are done with the cyclic compounds, and in the next class we will be talking about functional groups. So functional groups, we will be starting from the scratch. We'll be covering all the different type of functional groups, and because now we have learned alkene, alkanes, alkynes, and cyclic compounds, you may find the functional group on these structures also, because you already know the names of the cyclic structures and the alkenes and alkynes and alkanes. Just adding functional group, how it will change the name of the compound, that all we'll be learning in the next class. Till then, try solving the questions from the books. Ask me if you have any doubts. Solve the questions of the assignment and the module.